Hey, we're going to continue our discussion about diffraction and interference and look at a second equation to solve for the interference pattern. Before we go too far, I thought I'd show you in real life what diffraction grating looks like. Here's one right here. It's really just this thin little piece of plastic. Um, and let me show you the interference pattern. So I have here a laser. If I point that laser at the back wall, you can see for me, it's a nice purple. I'm not sure if it shows up too well for you, but there's my laser pointer at the wall. So in the interference pattern, we take a source of light and we put the diffraction grating somewhere between the source of light, and we'll call this the screen. The wall is the screen. So here it is without the diffraction grating, and now I'll put the diffraction grating in front, and you will see instead of just that central point, that one bright spot, we see beside it on either side the first order maxima, we'll call that sometimes, or the first point of constructive interference, a couple of points on either side of the central maximum. So that's kind of that interference pattern that you would see. If you got a little closer and took a look, and I can kind of see there is the central maximum, I can see the first order maximum, and then I can also kind of see a next order maximum, very faint for me to see. And if I looked even closer, turn down the lights, I could probably see another one. Let's see it with a different laser. Here it is with a green laser light. So same diffraction grating. By the way, if you take a look, there is, backwards for you there, but 530 grooves per millimeter. There we go. So if you take a look, there it is, and then I put the diffraction grating in front of it, and you can see how we produce these first order and even second order. If you look carefully, you can see a second order maximum as well. So it works in real life. It's not just a theory, and we're going to continue today looking at the second equation for interference pattern. So here's the second equation. It says lambda, or wavelength, is equal to dx over nl, where lambda is the wavelength in meters, still the same as the first equation. D, again, is the distance between slits in meters. So again, we have this diffraction grating. I'll refer to this picture down here. You'll notice that we have it. So again, the distance, in this case, they have S1 and S2 are the two openings in the barrier here. So that represents the D. So D would be measured between these 2 points here. X is the distance from the central antinode to the nodal line being studied. Again, this should be antinodal line. I thought I changed that, but it's the antinodal line. So on this picture, and in real life, when I shone that picture, you saw really bright spot in the middle. That's the central antinode, central maximum, if you want to call it that. And then the one right beside it would be the first one. So if we wanted to study the first antinode, we just measure from here to here. That represents our X. If we wanted to measure the second one way up here, we would measure X to be from there all the way to there along the wall. So in real life, it's pretty straightforward. You just get yourself a ruler and you measure, there's my central maximum, and then you just take a ruler and measure from the central to the first, second, third, whichever one you want to study. And of course, we can look at nodal lines as well, but it's more common, obviously, when you see this in front of you, you can see why it's way more common to look at the antinodes, the bright spots. They're easier to study. All right, continuing along then, if that's our X, N is the number we're studying. So again, in the case of these bright spots, we could number them. And if you did this, you might get a piece of tape on the wall and actually number these things and say, okay, this is n equal to 0. Here's my n equal to 1 on this side, n equal to 2. And again, we can think of the minimum as n equal to 0.5. Here, it would be n equal to 1.5. So n is the number of the antinode or node being studied. And finally, L represents, this is a little different from the last equation, L is the distance between the diffraction grating and the screen. So on this picture right here, it would be represented by this distance from here to here if I drew it nice and straight. In real life, it goes from where I hold the diffraction grating to where the screen is. Regardless where I put the laser, the experiment starts when the laser light hits the diffraction grating. Now we have our 2-point interference pattern starting here, and the waves interfere with each other and produce that interference pattern. So L is the distance between the diffraction grating and the screen. Don't confuse it with where this source is. The experiment doesn't start until we get to this point right here. So we measure from that point to the screen. So that's the equation. Again, I've kind of indicated that all these things are in meters, but the reality is because of the way that the units cancel in this equation, you really could use any units as long as they're the same. Then we'll get the right cancellation and we'll get our answer in the units that we choose, or for wavelength, it'll be in whatever units we choose. Yeah, so let's take a look at a problem just to kind of get a sense of how this looks. All right, so here's the question. The diffraction grating has 1,000 lines per centimeter. When red light with lambda equal to 750 nanometers is incident on the grating, what will be the separation between the bright antinodes on a screen 3 meters away? So, like I demonstrated here, how far apart would we expect these things to be? By the way, when we project this onto a screen, I should mention that most of the times the experiment is done in such a way that if this represents the screen, let's put it over here out of the way. If that represents the screen and I shine red laser light towards a diffraction grating, hits a diffraction grating somewhere around here, then that red laser light ends up producing a bright spot in the middle. It'll produce another bright spot along here, another bright spot along here. And as long as we do this experiment within reasonable parameters, usually the diffraction grating is quite away from the screen, then the distance between these x's is usually pretty consistent. So the distance between the 0 to 1 and the 1 to 2 is fairly consistent. It's usually the assumption that we make. So when they ask what will the separation between the bright antinodes be, then really we could find the separation between any of these and we'd know the answer to our question. Obviously, the easiest one to solve for is the first one, the distance between n equals 0 and n equal to 1, and that's what we'll do here. So as we gather information, let's see what we have. We have this 1,000 lines per centimeter. Remember, that's not the d, that is not the distance between the sources on the diffraction grating, but it's related to it. It's 1 over that value. So if you take 1 over 1,000 lines per centimeter, we're going to end up with units of centimeters between lines once we invert that. So that's going to be 1.0 times 10 to the minus 3. Now that's in centimeters per line. So we might want to further change that. Let's take a look at how everything else comes together. We have the wavelength of light is 750 nanometers. I'm going to write this like I told you before, 750 times 10 to the minus 9 meters. And we have the L. I usually use a little scripted L for that just to make sure I don't confuse it with any other numbers like a 1 or an I or something like that. So L is equal to 3.0 meters. So because my wavelength and length are in meters right away, I think I'll convert this D from centimeters into meters. I got to divide again by 1,000 or by 100. So 1.0 times 10 to the minus 5 meters is the distance between the lines. So there's all the information that we start with. So we give ourselves a little room here. So the equation that we're going to use is we want to solve for x. So we'll start with wavelength is equal to dx over nl. Where we're given the wavelength, it's 750 nanometers. 750 times 10 to the minus 9 meters is equal to d 1.0 times 10 to the minus 5 meters. We're trying to solve for the x, the distance between the bright spots. In this case, the distance between the first and the 0 bright spot. So we can put n equal to 1 here. And L is the distance between the diffraction grating and the mirror, or sorry, and the screen. So it's 3. So when I'm done, my X is equal to 22.5 or 0.22, we'll round that to 23 meters. So the distance between the points on the screen would be about 23 centimeters, probably similar to the experiment that I just did here, although I didn't have my diffraction grating 3 meters away from the screen. All right, so in our calculator, we end up with this 0.23. And similar to the experiment or the part that I did here, the little demonstration. So usually you get X's that are like 110 centimeters. You're not going to get meters or kilometers or anything crazy like that. Now, there's one thing we need to talk about with this equation. It's not quite as simple as just use this. Because of the way this equation was derived, it's actually not a precise equation. It's an approximation, and it works very well when you do the double slit interference pattern with light because of the small wavelengths of light. But we need to be aware that it has certain limitations. And the limitations are this. This equation only works when, big star, only for small angles. Now you might ask, well, what is a small angle and what's a large angle and how do we make a distinction? Well, less than, we need small angles. So angles less than about 10 degrees. So as long as our angle when we measure this is less than 10 degrees, we can use wavelength as dx over nl. If the angle is greater than 10 degrees, then we really need to make sure that we find that angle and use the other formula. So the formula that says wavelength is equal to d sine theta over n, that one is exact and works all the time. This one is, like I say, a small angle approximation, and you can get away with it as long as your angle is less than 10 degrees. Once your angle is greater than 10 degrees, you cannot use this. So that's the second equation for solving the interference pattern. So now you have two equations to choose from whenever you enter into these questions. Biggest thing in my mind is understanding what all the different variables are. There's a lot of them. And then some of the subtleties in terms of the wording of talking about an antinode or a node. So when is it n's are 1, 2, and 3, and when is n half, 1.5, 2.5. As you work your way through problems, you'll start to get a sense of this, and it'll start to become more second nature. You just get used to reading the question, really scrutinizing it. If I were to give one piece of advice, it would be this. When you do these questions, it's a good idea to kind of draw for yourself some sort of sketch of what's going on. So it never hurts to kind of give yourself a picture of, here's my screen, you know, before you get going. Here's my laser light or my monochromatic light or light coming in, producing a bright spot. So, you know, my n equals 0, my n equal 1, etc. You just want to kind of have a clear idea of what's being described in the question as you move forward. So the more concrete you can make it, the better. All right. Well, nothing you can do now except practice, practice, practice. So good luck with that.